the trick from the, you guys all watched the video I sent, right? Yeah? Do you like my pandemic beard? Yeah. It's not the best beard I've ever, well, it was terrible. I shaved it off after a while because it looked like crap. Anyway, so let's look at the trick basically that we use. So what we needed to do was to be able to flip the bits, okay, in order to do two's complement, uh, in order to start getting the two's complement representation, right? Because if you've got a number, how do you find its negative? You flip all the bits and you add 1. Okay, adding 1, well, that's easy. You just add 1. Okay, so that's not going to be hard. The flipping the bits part, however, is the question, because how do we do that using only those 12 operations? Okay, none of them say flip the bits. And so the trick is we need to think of a Boolean function that if you give it 2 ones, it gives you a 0, and if you give it a 1 and a 0, it gives you a 1. Okay, so that it flips the 0 or the 1 to the other thing. And which logical operation would do that? XOR. Okay, so if I take what's 1 XOR 1, XOR, not OR. What's 1 XOR 1? Okay, why is it 0? That's right, but why? Huh? Yeah, but XOR is not plus. Yeah, we built one of these things, right? Okay, and what was the whole point, the difference between it and a regular OR gate? Okay, a regular OR gate, if you had 1 or 1, the answer would be 1. Okay, do you have computer science and calculus today? True. Okay, do you want pumpkin pie or chocolate pie after Thanksgiving dinner? Well, okay, maybe Thanksgiving is the one, one of the days of the year that you can say, I'll have both, please. But, okay, normally if you're asked that question and you say both, you're going to get backhanded. At least that's what my mom would do. Okay. Um, okay, so XOR is the logical operation we need to use, and the pattern we need to use with it is a pattern of all ones. Okay, so I want to make clear here that it's not just using XOR that does the trick, because I have to XOR against something, right? I can't just take a number and XOR it against, well, there's got to be a second number there, okay? And so the trick really has 2 pieces: XORing against a bit pattern of all ones, okay? All right, so let's go down and let's look at this example, okay? So I'll blow this up nice and big. All right, so I've taken there, at the top row is the number 4. Okay, do we all agree that that's 4? Yeah? Okay. Mr. Burrish, you didn't show up late on Saturday, did you? Actually, yes. Actually, it seemed like the football team did kind of show up a little late. Yeah. Well, thank you for finally showing up in the second quarter. And they drove back to Greencastle in the second quarter, apparently. So, although, actually, speaking of the game and the shenanigans, I've been both face palming and laughing my butt off about this free Melch thing. Well, okay, the public indecency part, I don't think will stick, right? I mean, a bikini reveals more than that, right? The public intox part, he's on his own for that one. Me? Absolutely not. If I were that plastered, then yeah, that's not an affirmative defense, however. That too. Okay, yes, there will be some lawyer alum. I mean, we saw this during the last attempted Bell heist, um, which, my understanding is that there were two pieces where they failed. One, they didn't know about the pressure sensor. And although, if you've seen Indiana Jones and the Temple of Doom, you'd know how to solve that. Okay, right. Yeah. Uh, so yeah, you could have done that, right? But then also, I think the getaway car had its lights on the whole time, and so like one of the security guys was like, "This is sketch," and was just like, "I'm just gonna sit here and watch." And then all of a sudden, guys in costumes and masks come hauling a bell out of and he's like, "Gee, I wonder what's going on here." So they didn't make it to the car. you know, yeah, it was over pretty quickly. So, um, yeah. Anyway, um, yeah, yeah. Don't streak. Streaking's bad. Okay, and he didn't even really streak. I mean, right? I don't know if that's the best part. Yeah, that in that sense, it's a good outcome. Yeah. Um, okay. So, sorry, where was I? So we've got the bit pattern of all ones there, and we've got the number 4, and I want to flip the bits, okay? And so if I XOR this, now that does it bitwise, okay? So first bit gets XORed against the first bit, second bit against the second bit, third against the third, and so on, okay? So do you guys all agree that the only bit that actually flips here is the third bit? Um, because 1 XOR 1 is 0. That's the opposite of 1. Okay. And, sorry, well, they all flip, but, okay, the rest of them flip from a 0 to a 1 because 0 XOR 1 is 1. Okay, so do we all buy that? Yeah? Okay, so that's the flip the bits part, right? So this result, the bottom line there, is not the representation of -4, is it? Okay, because we still have to add 1, right? So if I add 1 to this, what do I get? Add 1 to this. What do I get? What happens here? 0, carry, 0, carry, 1. So I'd get 6 ones followed by 2 zeros. We? No. Okay, so, and what did I say? Yielding the final pattern of that. Okay? Okay, so that's the trick for how you negate a number, right? And this is why when we did the two's complement stuff, I taught you guys to think of it as to flipping the bits and adding 1 bit, okay? Because of this trick right here, right? That's an easy way to think of it in terms of implementing it in this sort of model programming language. Now, I actually did learn something the other day um, that I don't know why it didn't dawn on me until just now. Um, let's take the number that we got that represents -4, and let me show you guys a trick. Okay, and I learned about this because, well, I didn't do absolutely nothing this weekend. I was in bed the whole time. But when I was awake, what did I do? I sat around and watched videos on YouTube and catched up on TV on Paramount Plus and so on, right? And one of the YouTube videos I found was actually a guy who was building a full-blown computer in Minecraft, like using redstone and pistons. Okay, and that was pretty cool. But he had a way to think about two's complement that I've never run into before, and I thought it was really clever, so I thought I'd share it with you guys. Well, clever slash maybe obvious depending on your perspective. Okay, so if I want to know what that number represents, okay, up until now, how would we have done it? Yeah. Yeah, okay. So if it was an uint, we'd say we'd have the 1, 2, 4, 8, 16, 30, and so on, right? Okay. And if it were a uint, we could just do that and that'd be fine. But we couldn't do that if this were an int because this number is clearly negative, right? Because its far left bit is a 1. Okay, so what did I teach you guys to do instead? If you encounter that, then what? Flip the bits and add 1, see what you get, and then say, oh, well, then what I had must have been the negation of it. Okay, does that make sense? Here's an easier way. If it's a uint 8, what are the place values? 1, 2, 4, 8, 16, 32, 64. And if it's a uint 8, what do we put here? 128. Excuse me. So that's the same as before. Nothing's changed there. Okay. Here's the clever bit. If it's an int 8, think of this as not the 128th place, but the minus 128th position. And then do like normal. Okay. So let's add all this up. What do we get? We'd get negative 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2, or no 2, sorry. Okay, and then we just got to add all this up. Now, of course, we know what it's supposed to add up to, right? It should be minus 4, but let's just double check. This is 64, minus 64, sorry. That's minus 32. That's minus 16. So we've got minus 16 plus 8 is 8, negative 8, sorry. Plus 4 is negative 4. Yes, it does. Okay. Well, okay. It always works. Okay, and here's the nice thing, okay, about it that I think maybe is what makes this way of thinking about it a little bit more useful. What were the 2 bit patterns that if you flipped them and added 1, you got the exact same bit pattern back? Okay, the negative 128, the most negative number, and the bit pattern of all zeros, which represented 0. Okay, the second one, all zeros, that made sense because what's negative 0? Yeah, right. There's no difference between positive and negative 0. Okay, so that one made sense. But the minus 128 one, remember, was a little weird. Well, if you think about it this way, then if you've got a 1 followed by all zeros, then isn't it obvious that it's minus 128 as a uint? Or sorry, as an int? Yeah. Would you guys agree that's much easier than what I taught you guys the first time? Yes. So, mhm. Well, I would hope, Cody, that you'd be able to get it right no matter what bit pattern I put here, because I've, you know, figure out what the value of a negative number is with this one weird trick. Oh, come on. I don't get anything out of that one. Like internet ads, right? Lose 5 pounds of belly fat with this one weird trick. Huh? Yeah, I hate those ads too. Um, Actually, I read a really interesting story where an investigative reporter basically did a deep dive as to the one weird trick empire, and it all goes back to like this one dude. Um, it's kind of like I read this really good story on Ars Technica, and then they had a really good follow up about a guy who basically took a freelance job for a unnamed online media company. And basically, his job was to come up with like some automated systems for uh, basically posting as much disinformation as possible, uh, and figuring out like what type of disinformation spreads the fastest at different times of day, and also like how do you intersperse real content that's maybe not disinformation, things that don't really actually mean anything, like puppy pictures or something. Like around lunchtime, you send out cute videos of animals, but then 4 hours later, you're like, these people are destroying the country and stuff. And yeah, anyway. Yeah, well, and that's exactly what I was doing it, right? Was playing into the psychology of people's sort of workday and kind of what content they want. But also, if you see cute puppy pictures from a thing that's also spewing, you know, misinformation, uh, you're maybe like, it's almost like, did you ever have to take foul tasting medicine when you were a child? Right? And if like there's a little sugar or honey or something with it, then maybe you can get the kid to swallow it a little easier. I guess it's kind of the same principle, right? I mean, heck, even Lucretius writes about that trick. Um, you guys know who Lucretius was? No, nobody. Do I have any PPE majors? Yeah, you never heard of Lucretius? Yeah, actually, I highly doubt you would have in PPE, but that's okay. He didn't really write about economics or politics, but anyway, he wrote about atomic theory, and he was a Stoic. Uh, yeah, so but like Greek atomic theory, like before there was actually any experimental evidence for atomism. So yeah. Um, okay. Anyway, um, so uh, this trick, okay, with this putting the minus 128 or the 128, depending on whether or not you're doing a uint or an int, works great on paper. Okay, so here is the utility, though, of the flip the bits and add one kind of view of it. Namely, that's what we'll program on this computer thing. Okay, because um, we've cracked the trick, which is you XOR against a bit pattern of all ones. Okay, so sorry. Okay, so let's write a program. Okay, that and in fact, let me just start a new document. Let's see, Office Writer. Actually, I don't know why I'm doing it there. Let me do it in an actual IDE. Okay, so what we need to do here is I want to write a program using those 12 instructions that will take two numbers and subtract the second one from the first one, okay? And let's suppose, first off, that the two numbers need to be in memory someplace. So let me say that they're in memory cells FD and FE, respectively, and then I'll put the answer in memory cell FF. Does that sound good? Okay, so program to take let's see, I'm not the only guy with the frat flu that's going around. Turns out everybody drinking beer out of the same bell is a monumentally good way to spread disease. I don't know. Some of those consequences might keep on consequencing for, huh? Yeah, I hope he was. And if not, he sure is now that he's sobered up. I bet he had an interesting conversation with the dean of students on Monday morning, uh, assuming he was out of jail. How much was the bail for that, by the way? Did he have to post bail? Oh, okay. They put him in the drunk tank. Okay. All right. So Tuesday morning. Yeah, I would. Uh, all right. So first thing we've got to do is load the two numbers into registers someplace. Okay. So how do I load memory cell FD and put it in a register? Okay. Now let's be careful because how many different load instructions are there? There's two versions. Which one do we want? Okay. So we want this load instruction, and sorry, I really need to put a mute button on here on Discord. I mean, Twitch. You guys don't have to listen to me hacking. Yes. Uh, which one? Well, let's go back up to the list. Okay, which one do we want? Opcode 1 or opcode 2? Opcode 1. Okay. Now, the reason that the 1 is here is what register do I want to put this data into? I could put it anywhere, but I'm choosing to put it in register 1. Okay. So the opcode here would be 1 to put it, or is the operation. Okay. Move memory to register. Which register am I putting it into? 1. Which memory cell did it come out of? FD. Okay, so what I'm doing here as I go, okay, is making what's called a listing, okay, and a listing has sort of 3 or 4 columns depending on how you want to think about it. The first one is going to be which memory addresses the instructions go into, okay, and where's the very first instruction have to go in memory on this computer? They have to go in 00, the first one, okay. The second column, so where I've got 11FD, that's the actual instruction, okay, encoded for this machine. And then the third column is the assembly code. That's just sort of human readable part, okay. And then if I want to put comments, then I could put those in, and that would sort of be the fourth column, if you will, okay. Okay, so which one of those did I write first, though? Or type first, maybe? I typed the load 1 comma FD first, right? So I did the human readable part first, and then I put the other two parts in when I was finished, okay? Now, my suggestion is don't put the far left two columns in until you're basically finished writing the thing. Okay. For more complicated programs, that will save you trouble down the line. Okay. For something simple like this, I'll just kind of do it as we go because, well, I'm pretty good at this, and it's not that complicated. Okay. So, all right. So I need to load the second number into another register. Okay, so I'll put the second number in register 2. That's fine. And would you guys agree that the instruction would therefore be 12FE for this? Yeah. Okay, it kind of helps. If you've got your computer open, pull up the little sheet that's got the list of instructions and kind of keep that in front of you. Um, And by the way, you'll get a copy of that sheet of instructions for the final, right? Because I don't expect you to memorize all of them. That's pointless. Um, Although I think you guys will notice that you'll start to memorize some of them kind of by osmosis, but yeah. Okay, so I need to do that. All right, now what's the next thing I need to do? If I want to subtract a number from another number, I first have to find its negative, okay? So in order to find its negative, I've got to use the bit pattern of all ones with the operation of XOR. Well, I kind of need the bit pattern of all ones in my computer someplace, right? So let's load that in first. Okay, so 2 questions here. What's the difference between opcode 1 and opcode 2? And what's the difference between a $sign and a hash mark? Yes. Yeah, that specific number, okay, FF, whereas the $sign means whatever's in that memory cell, okay? We're good there? And then what's the difference between opcode 1 and opcode 2? Opcode 1 does what? It takes the contents of a memory cell and puts them into a register. Opcode 2 takes a specific number and puts it into a register. Okay? And in this case, the number that we've chosen is FF because that's the bit pattern of all ones. Okay? Okay. I need to what do I need to do next? I need to do the XOR. Okay? So what is the opcode for XOR? Well, it's this one. Okay? All right, so it's opcode 9. All right, so this will be 9. Well, which register do we want to put the answer into of the XOR? We could put it anywhere, but how about 4? Okay, and which 2 registers am I XORing together to get the answer? 2 and 3. Okay, so this will be XOR registers 4, 2, and 3. Okay, so what's the convention here? The 4 is the destination, and that's listed first here. Okay, is that maybe a little backwards from how you'd expect it? Maybe, but sorry, that's just the convention. Okay, good. Okay, so we've XORed it, and that answer is sitting in register 4. What do we have to do next? So XORing it flips the bits, then what? Yeah? Okay, in order to add one, we first need to have the number 1 available to use. So I need to load register 5 with the specific number 1. right? Because I can't just pull 1 out of thin air. And now I can add it. Okay, pop quiz. What's the next memory address? Okay, so you see I've got 020, 02, 04, 06, 08. What's the next one, Cody? I'll give you a hint. It starts with a 0. Nope. Nope. 0A. Because it's in hex, remember? Yeah. Yeah, I remember. You need to get you some member berries, right? But I don't know. Maybe eating member berries is bad, okay? Okay. All right, so it's 0A because we're in hexadecimal. All right, so I need to do the addition. What's the operation for addition? Well, there's 2 of them. Which one do we want? Yeah, we want the integer version, which would be this guy. Okay, so which 2 registers do I want to add together? I want to add 4 and 5 and put that answer someplace. So what would be a good destination? Where should we put the answer? How about 6? All right, and so the opcode for that is 5. We're doing 6 and 4, 5. Okay. Okay, so now what is sitting in register 6? It's the result of flipping the bits and adding 1. Isn't that what we called the negative? Okay, so if I wanted to subtract the value that was in memory cell FE from memory cell FD, we've just computed the negative of whatever was in cell FE. Okay, so if I want to do the subtraction, what do I really do? I'm doing addition. So I need to take what's in register 1 and add it together with what's in register 6 and put that someplace. Okay, so let's put it in register 7, and we're adding, what did I say, 1 and 6? Okay, so now what's in register 7 is the result of the subtraction. Okay, what did I say we wanted to do with this answer? I wanted to put it in cell FF, so how do I do that? Well, which operation do I want? This one, okay, opcode 3. So it'd be 3, register 7, memory cell FF. And after we do that, then what? Are we finished? Basically. Yes. We just need to halt. Okay? All right, now, what I'm going to do is I'm going to take the column that has all of the instructions and just put them all in one line. So 11FD, 12FE, 23FF, 9423, 2501, 5645, 5716, 37FFC000. Okay, so I'm going to take this and I'm going to copy it. Okay, so before we go to the web program, any questions here? We good? Okay, so now like I said, what I did there was I took all the instructions and I just wrote them all in one big line. Okay, and the reason I did that is because if we go to our website, or Joel's emulator, okay, and then I put a pound symbol and I paste in what I just had. I hit enter and then I refresh the page. Notice that all of the stuff that I just typed or pasted in has been loaded into memory starting with cell 00. Okay, that's a pretty quick way to put data into this thing, right? Because then you don't have to type it into each individual memory cell. That makes things a lot easier. Okay, so in order to run this, though, we need two numbers that we were going to subtract, and they've got to be sitting down there in cells FD and FE. So pick some numbers. Cody, give me a number. All right, big shock. Uh-huh. Which is actually 105, right? Because this is 69 in hexadecimal. Mm-hmm. Of course, right? Okay, so we'll make that. Oops, sorry, that's the wrong spot. Yeah, that's what your mom said. So, okay. Yeah. All right, so we need another number to subtract from 69. Huh? 4F. Well, actually, you know what? Yeah. Okay, so 4F represents the decimal number or base 10 number 79. Okay? All right, so basically we're doing 105 minus 79 here. Good? All right, so let's run it. Okay, and watch as this happens. We're loading in data. All right, flip the bits, put in 1, add 1, do the subtraction, store it to memory, halt. Okay, so what did we get as the result of our computation here? 1A, which is what? If I hover over it, 26. Is that 105 minus 79? Yeah, it works. Okay, wonderful. Isn't this great? Okay, so excellent. Now, let's go back to the notes, because now we get to talk about the fun part. Namely, there's one instruction that we really have not done or used at all yet, and that's this one. This instruction is what makes this a computer as opposed to just a stupid calculator. Okay? It's the ability to make a decision and do one thing if one thing happens and something else otherwise. Okay? So, in terms of when we were doing, looking at sort of very, very simple Python stuff, right? Or really the fact it was Python is not relevant. We were looking at stuff that started with if and had a condition, and then there was a thing you did if the thing was true, right? And there were else's and that sort of thing, right? This instruction is what enables that and also looping if you use it right. Okay, so that's the instruction I want to start talking about now. All right, so let's go down here and find where I've got this. Okay, so here's the syntax for it. The instruction name is jump. It needs two pieces of data to operate. It needs to know which register to take a look at, and if the jump takes place, it's going to jump to a different cell of memory to start loading in the next instruction, okay? So basically what this does is, so let me go back to the emulator, for example. We talked about the program counter. What's the purpose of the program counter? What does it do? Any day now, gentlemen. Huh? Count how many things you're on. No, not really. It points to where the next instruction in memory is to be loaded from. Okay, so what's the initial value of the program counter before we do anything? Should be 0, 0, because where do all programs start here? Okay, so what the jump instruction can do is change the value of the program counter. Because if I change the value of the program counter, and the program counter represents where the next instruction is going to be coming from, if I change it, then what the next instruction is has now also changed. Does that make sense? No. Okay. Huh?
Like if you change it to 0, 0, just run the same thing you did.
Yeah, okay. So for example, all right, so let me actually demonstrate that. Let me replace the C00 here with B000, okay? All right, now, there's really two things that are gonna make that happen. This instruction does not always change the program counter. It only does so if register 0 is equal to whatever register I specify here. Okay, so how can I make this always happen? Well, if I compare register 0 to itself, is it always going to be equal to itself? Yeah, I would hope so. Okay. No matter what's in it, it's still equal to itself. Okay, so doing this is actually an unconditional jump. It will always take place. Okay, so if I run this, watch what happens. Okay, so watch the instruction counter I see up at the top. Okay, so what just happened? It basically reset, but it didn't really reset in the sense that I never stopped program execution or hit the reset button kind of thing. What it did is it looped back and started loading in the instructions from cell 00 again. So what is basically the program trapped in now? It's an endless loop. Okay, it will never terminate. Now, is that a good thing to have an endless loop? In this case, probably not, right? Okay, and so we've sort of coded this poorly. I mean, sort of deliberately here for the sake of demonstration. Okay, yeah. Now, watch if I change. So let me stop. There is actually no stop button on here. You have to actually just hit refresh. So let me change this to B0, and I'm going to change it to, I don't know, how about 20? Okay, now watch what happens. Okay, so most of this is the same as before. Okay, what happened to the program counter when it encountered the instruction B020? The program counter got changed to 20. So the computer said, okay, I'm going to go fetch the next instruction from memory cell 20. Well, what's sitting in memory cell 20 and 21? Just all zeros. Are those a valid instruction? Huh? No, they're illegal, right? Okay. Much like much of the content at the football game, or rather outside the stadium of the football game, um, and much like the DePaul uh, football team's performance after the second quarter. Okay, I don't know. Like, you look sus today. Yeah, look at the colors you're wearing, man. And black and yellow. You guys are worthless. Okay, so you have to be careful here because if we jump to a um, a bad spot, right? We've got to be careful to select what memory address am I jumping to, okay? But also which register am I comparing to register 0? Now, if I compare register 0 to itself, like I did here, will that always jump? Yes, okay. So in this case, this is what we call an unconditional jump. There will be ones, and we'll talk about these, I guess, next time, that are conditional, where they sometimes happen, but not always, okay? And that's putting these two things together is how we can construct if then else statements, for loops, and while loops, and also, I guess, do while loops, okay? Right, so we can get all of those basic pieces all from using the jump instruction or maybe a couple copies of it and using them correctly. Okay, does that kind of make sense? Yeah? Okay, so Friday, what we'll talk about is if then type statements and loops that are actually useful instead of this sort of deliberately endless loop. Okay? And like I said, I hope to have your exams graded and stuff uh, by this afternoon so you can swing by and pick them up. Uh, the retake procedure on Friday will be exactly the same as it was last week. Okay? I don't know. That offer maybe only applied last week, right? All right. See you guys later.